the next half hour, I'll tell you about stuff that has been implemented, and I know it because I wrote both. The first is a very simple heuristic, very simple and very fast, and for this reason not extremely effective, but effective in a sense. I wrote it for the Couenne solver, and so it was written long ago. The second one is a similar heuristic, but it uses, it was written for nonlinear optimization problems and not mixed integer, so continuous nonlinears. Couenne's heuristic is one of the small projects that I thought was not extremely important for the performance and or for publishing purposes. And it was written long ago in one night, pretty much. It's basically 300 lines of C++ code. It's the only default heuristic in Couenne. Couenne is this MINLO solver that I wrote with other people in 2007, 2008, and it's for non-convex mixed integer nonlinear optimization. So it uses all the stuff that Sven talked about yesterday. So reformulation, the computational graphs, so the expression trees, etc. And it does spatial branching. It has convexification cuts, so that sort of linear relaxation for approximating non-convex sets, such as y equals x cubed, for instance. We can have a look at it. I don't think it's really important, but given that we talk about this code, that's here in all its glory. So it's literally a very small loop. If I can find it. Yeah, there it is. It's a loop on all the variables, but it looks at variables with a certain idea in mind. And the idea is to try to understand how to go from the solution to a continuous relaxation, even worse, the solution to a linear relaxation of a MINLO, which does not satisfy integrality on the variables and does not satisfy even the nonlinear constraints. This is obviously going to give you a solution that is not that is far away from feasibility for both integrality constraints and nonlinear constraints. But it's quick and it's fast enough that it's used in basically every branch and bound node. Just in case we are lucky enough that we just take one point that was found through the branch and bound, and it's close enough to a feasible point that we find it easily. So I'll write a slightly different version of MINLO where I put a lot of emphasis on the bounds on the variables x. Here, x is just a vector of variables that has both integer and continuous components. So the first p variables are integer, the rest is continuous. There are m constraints, all of them are nonlinear. The objective function is linear, but by now it should be pretty clear that whether our objective function is linear or nonlinear doesn't really matter. If it's nonlinear, you just move it to a constraint by adding an extra variable. All the functions g, all the nonlinear stuff appearing in the problem is factorable in the sense that we know its expression. It's a closed form. We can create a graph, an expression tree for each constraint, and this expression tree is made of nodes representing operations from a finite set. Plus, minus, multiplication, division, powers, exponentials, logarithms, signs, etc. So at least we know that information on the problem. And this is a repetition of what Sven said yesterday, but the reformulation does exactly that. And the reformulation has a lot of consequences on the problem itself. Not only it is necessary to create convexification cuts, because the convexification of each term is basically done on the auxiliary defining that single node. For example, this node will have, I hope it's visible enough, this node is the square of its argument, and the argument is y, and the auxiliary variable associated with it is w3. Not only is this necessary to create convexification cuts, which we'll talk about later, which we won't talk about in this talk because they're simply not important. It also gives us a very good structure to explore for doing bound reduction, which is also something that you learned yesterday. Bound reduction is an extremely important part of any MINLO solver, both convex and non-convex, but especially non-convex. The reformulation part is the one that you see here. Again, this is a very simple problem, and you saw the reformulation part before. I wanted to write this because there's another trick that maybe has nothing to do with this talk, but that is also useful, that it can be also useful in MINLO. You see here, there is a nonlinear objective function x plus cosine of y. And then we have that x is greater than or equal to y squared times z to the fourth. Following all the steps of the reformulation you learned yesterday, you would think, okay, so x is just by itself. Cosine of y, we define a new auxiliary variable w2, which we want to be cosine of y. That's fine. And then we have y squared. We create a new auxiliary variable w3, which is equal to y squared. Z to the fourth is associated a new auxiliary variable w4. And in principle, then you will have to say, you will have to create, and I didn't, on purpose, another auxiliary variable. Where did we get? w5. You should have, we should have had in principle another variable w5 that is equal to what? The product of, well, y squared times z4, associated respectively to w3 and w4. So we multiply them together, and we would get another auxiliary variable for this product term. This would be the standard reformulation. I'd like to point out two things. If we had that the first constraint was something like x, okay, w squared z to the fourth equals x, and right now is less than or equal to x, then, you know, once you reformulated y squared and z squared, creating a new variable y5 just to say that this is equal to the product of the two auxiliary variables and just leaving x as this new auxiliary variable doesn't really make any difference. Actually, it's perfectly fine to do this in a MINLO solver, and it's even better because, first of all, you have one less variable, because then obviously you would have to say w5 equals to x, which is fine. Most solvers see this sort of constraint, they laugh at you, and then they just eliminate one of the two variables throughout the problem. This is clearly obvious. This is the first piece of information. So we just save one variable by not doing by not following the standard reformulation. The second part is the following. We don't have equal here, we have less than or equal to. And in fact, the reformulation, once done in a standard way, would result in this other constraint. But it's also true that if you have a constraint of this form, you're basically saying, so x needs to be above a function that is expressed like this. Or in a sense, instead of having one auxiliary variable that we need to take the convex envelope of, we actually need to take just one side of the convex envelope. So if you had this function like this, with this lower bound, this is the argument, let's call it t, from 1 to 5. And this is the function over t, and you had an auxiliary variable v that you want to be equal to f of t. If you follow the standard reformulation step, what you will have is create a new auxiliary variable for the function f of t. F of t is a function expressed by a single operator, but we don't care about that much. And then the next thing to do would be to create linear constraints, or linear constraints that approximate the convex envelope of this non-convex curve. So ideally, you would try to find this convex envelope. So this convex object in this space. This is because you said, no, I want this auxiliary variable to be equal to this. You can't do it because this is a non-convex set, so you try a non-convex set, so you try to find the convex envelope of it. Suppose now you instead of having V equal, you have V lesser equal, because this is precisely the condition we want up here. That is, we want x to be greater than or equal to something. Then, in principle, you don't really care to get this upper envelope. No, V lesser than or equal to, sorry. So you don't care about getting the lower envelope. All you care about is really getting this set of constraints right. The rest you don't care. You actually want this sort of envelope. Whether you take this bigger set or that subset doesn't really matter, because it's for whatever auxiliary variable here, a less than or equal to constraint is just fine. This saves you, however, a lot of linear inequalities that you would have to add if you wanted this bottom part as well. So two things that Couenne is not a very clever software. It has a lot of things that were written by somebody who didn't know anything about nonlinear mixed integer nonlinear optimization. Didn't know anything about mixed integer linear, didn't know anything about nonlinear, didn't know anything about mixed integer nonlinear at the time. And I mean, that's me. And I learned a lot since then. But Couenne was written this way, so it has a lot of very simple stuff. But this has worked surprisingly well. This is one of the few smart things that are in Couenne. Now, this was a digression from the heuristics, but it should tell you that it's very important to convey and use all the information you have from your expression tree. You should have noticed also that this is not exactly a tree. And in fact, the set of expression trees for all the constraints, they are not trees but graphs. But they are directed graphs, and they're also acyclic, simply because it's basically you take a bunch of trees and you put them together, and they are connected at the leaves. This helps you because obviously if a function is a function of a variable y, and then there's another function that's also a function of a variable y, clearly those two will point to the same node y in the directed acyclic graph. So we call him DAG simply because it's a bit shorter. So this is your reformulation. Notice again that since I didn't want to use another auxiliary variable, I have the node corresponding to the variable x up here, because x is now associated to the node that multiplies these two other guys that are associated with auxiliaries W3 and W4. Ambush question. What's the optimal solution of this problem? What is x and what is y and what is z? Mine, no, all the variables are integer and between 0 and 3. So you were saying the value of the optimal, the value of the objective function. The best objective function value is 2? Mm-hmm. Yes. So from a vantage point of knowing already a lot of mixed integer nonlinear, we have an optimal solution of 0, 3, 0. So we want to minimize cosine of y. So we want to push y as much as we can towards pi halves, towards pi. So if y is equal to 3, then cosine of y is not exactly -1, but it's close to -1. And then we simply need to say, okay, x needs to be as low as possible, so it can be 0. But in principle, y is already non-zero, so we need z to be 0 as well for this to happen. Z doesn't appear in the objective function, so the optimal solution is 0, 3, 0, and the objective function value is about minus 0.9, something like that. Do you agree with this? This was also a digression, but I want you to notice this thing. This is a DAG for a very simple problem, and the way the bound reduction works, which is the fundamental component of the heuristic, is by exploring this DAG up and down. And in many of the papers about bound reduction, you will notice that bound reduction is simply done by taking the bounds over the on the variables and propagating them up until you get a bound on this, which is the objective function, and that will give you valid lower bounds and upper bounds on the objective function. The crucial thing, the crucial thing about bound reduction or bound tightening or domain reduction is that applied to an optimization problem like this, if you give it a valid set of bounds on the variables, it will give you possibly tighter set of bounds on the variables. They're all valid. That is, they retain at least one optimal solution of the problem. So it might be the case that some optimal solutions are cut, some global optima are cut, but at least one global optimum is going to stay in that bounding box. So in this sense, bound reduction algorithms are exact. They're not heuristics. They really give you a tighter bounding box. And it's really, so they are really useful in that sense. And they are crucial in every MINLO solver. They are pre-solved mechanisms. They are like pre-solved mechanisms in mixed integer linear where they are extremely useful. The other thing is that this is a graph exploration algorithm. So it's extremely fast. Even if you have a very large problem with thousands of variables in complicated expressions, that will give you a DAG of tens of thousands of nodes, where you can still run a graph exploration on a graph that big in a relatively short time. So bound reduction is fast. It's exact. It doesn't chop off all optimal solutions. It still keeps some of them. And it's extremely useful. The techniques for bound reduction come from a lot of different disciplines. And in the case of Couenne, the reason why I wanted to write a heuristic in this form was the following. We suppose now that we have one point that is the optimal solution, the globally optimal solution of a linear optimization relaxation of a MINLO problem. So we relax integrality, we relax some of the nonlinear constraints. We get a solution that is feasible for neither the nonlinear constraints nor for the integrality constraints. So in some way, we need to take that point, and if we don't want to use complex function, and if we don't want to use complicated procedures in the software, we need to somewhat use bound reduction. The way we do this is by looking at the DAG and see what variables we can change first. As you can see here, there are many variables in a reformulated MINLO problem. The fundamental variables are the y and the z, in this case. If we change them, specifically, if we change their bounding box, they are bound intervals, for each variable, there's going to be a cascade knock-on effect on all the other variables, on all the other auxiliary variables in the DAG. So rather than change the bounding box of any variable in the DAG, we start from the leaf variables, so from the original variables of the problem, because we know that changing their bounds is perhaps going to change a lot of other bounds. So they are the most consequential variables, and probably the only ones for which we can change the bounds. And this tells us that in a DAG you have classification of sorts of the nodes. You have leaf nodes, and those are usually, well, the constant, if you use constant in a DAG, and the original variables. Then there's the root nodes, and you have one for each constraint. Each constraint has a root node under which is its expression tree. These nodes are not exactly do not have any operator associated to them, but they have a bounding box, because if a constraint is of the form g of x less or equal than 5, then that constraint node has a bounding box of negative infinity 5. The objective function as well has a node associated to it, and we can associate to this node a lower bound and an upper bound in case it's of interest for the bound reduction, and it is always of interest. So basically what you do is we classify the variables according to their rank, and in a more systematic way we can define the rank of a node in the DAG as you take that node, you compute the distance, the shortest distance from that node to any of the bottom of the leaf nodes, and that is going to be the rank. The rank tells you how much that node depends on the nodes underneath, and especially a change in the bounds of the nodes underneath. And that's the idea. Use the rank to sort, to give you an ordering of the variables before applying some form of bound reduction and probing. Does everybody know what probing is? Yes. Exactly. Why? That is correct, because a change of bounds in y will trigger a change of bound in x. Even if x is an original variable. Very good observation. So before we return to the next slide, raise your hand if you know what probing is in mixed integer linear or mixed integer nonlinear. Wow. Okay, probing is a very simple algorithm. It works very well on binary variables, and it basically says the following. You have a problem, you have a mixed integer linear problem. Let's start from this simple example. With a lot of binary variables. There are very many, and the problem as such may be difficult to solve. However, you want to understand, you would like to find out that whether you can fix some of those variables. So you do the following. You take every binary variable, you fix it to 0 first, and then you run, for example, you try to solve the linear relaxation of that problem with that variable fixed to 0. And suppose this tells you x0 is fixed to 1. It tells you that the problem is feasible. The optimal solution z star is equal to 4, etc. Now you unfix the variable x1 and you fix it now to 1, and you run the same thing. You run again linear relaxation. You solve a linear relaxation of the problem. This time the problem turns out to be infeasible. What does that mean? Very simple. The problem is still there. You didn't solve it, but at least you know that x1 must be set to 0. So you eliminated one binary variable just like that. So you repeat this for all the binary variables. You may end up with some of the binary variables fixed to 0. So you may end up with a lot of much fewer variables than you started with. The concept itself is very simple, right? Is it clear to everyone? And you can obviously do this for, yes? Mm-hmm. So if setting x1 to 1 gives you an infeasible problem because you solve a relaxation, but the the linear optimization relaxation tells you no, this problem is infeasible, this implies that x1 is equal to 0, right? Is equal to 0 for any integer feasible solution. If you repeat this for all variables, some of them may just be such that both fixings give you a feasible problem. In which case, oh well. What happens if fixing x1 to 0, x3 to 0, and then x3 to 1 give you both an infeasible problem? The problem is infeasible. And it may not appear from a linear relaxation simply because the linear relaxation has had x3 between 0 and 1 with all the continuous solutions in between. So if this, for instance, was if this is x3 at 0 or at 1, the linear relaxation would easily be found to be feasible. So the polyhedron is obviously not empty. But if you fix x3 to 0, you get nothing, and you fix x3 to 1, you get nothing. So the problem itself is integer infeasible. Okay, so probing does exactly like this. There's a variant. There are many variants, actually. So what I said here is that after fixing the variable to either 0 or 1, you solve a linear relaxation of the problem. Well, you do whatever you want with that, and if you do it with linear, if you do solve a linear relaxation after fixing one variable to 0 or to 1, what you get is something called strong branching, which I think we talked about briefly during the course. So this is a very nice method of understanding which branching variable is best for deciding what branching rule to enforce in a branch and bound. But again, this requires you to solve a linear optimization problem after fixing any variable. If you have many variables, even if you filter them a bit and you just arrange just a small set of candidates, this is still a lot of linear optimization problems. What I did for this nice heuristic was, don't solve any linear relaxation problem, just run bound reduction. So you take again the DAG, you fix one variable to 0. You run bound reduction. Who knows, maybe bound reduction will tell you, no, look, with bound reduction I can prove that this fixing gives you a new bound interval for variable x4 that is empty. So x4 would have no feasible value that satisfies that condition for x1 equal to 0. The problem is infeasible. We need to set x1 to 1. This is probing mixed with bound reduction, and this is precisely what the function does. It does it not in a random way, so it picks the variable one by one in an order defined precisely by this rank. So it takes variables of rank 1 first, of rank 0 first. So first it takes all the most of the original variables, the ones with rank 0. It tries, well, among them, of course, it only takes the integer variables, and it tries to round them first down, and then up. It runs a bound reduction on such fixing, and it tries to see what happens to the problem. So you can see here, for every natural number r, let's take the set I of all non-fixed integer variables that have rank r. And then, in order to just maintain some simplicity in the scheme, even if a variable is integer instead of binary, I still restrict its interval between its rounded down value and its rounded up value. That may actually be counterproductive because it may actually cut off every optimal solution. But I don't care, and if it happens, well, so be it. And then for every such already tightened set of fractional variables, again, I do some sort of probing. So you fix xi to its rounded down value. We run bound reduction, and we get a new problem PDN with new bounds, new bounding box, and then we unfix it. And then we do the same by fixing xi to its rounded up value, and we do the same. So we get two different problems. This is just for notation. I don't actually create two new problems. I simply I think you just need an integer for that. If both problems are infeasible, that means it was not a good idea to restrict the bounds to the rounded down and rounded up value of xi bar. And we just stop and we give up, and this run of the heuristic didn't give anything, forget it, let's move on with the branch and bound. However, if If one of them is infeasible, obviously you fix the variable to the rounding, to the opposite rounding. And even better, if you manage during this bound reduction to actually limit the bounds so much that many of them, all of the integer non-fixed variables return an integer solution, it might actually be an integer feasible, so an integer solution and a feasible solution for the nonlinear problem. So you might actually just find a feasible solution like that. So you run it until you have patience and possibly for all the variables in ranking order. Obviously, you stop after k iteration because you don't want this to run forever. This is what was, as you can see, the algorithm is extremely simple, and that's why it could be, I mean, it's implemented in 300 lines of code, including comments and including, all the calls for bound reduction, which obviously is done elsewhere in the code. But it's, if you run Couenne with this simple version, on the library of instances called minlplib2, which is a very important library of instances, you get a feasible solution in, almost 60% of these instances. And it's extremely simple. A very important thing which I didn't say before is that finding a feasible solution for a MINLO is extremely important for several reasons. First of all, in a branch and bound, it's very nice to have an upper bound, a cutoff, that can help you eliminate vast portions of the feasible set that are not as promising as the feasible solution you just found. So finding a feasible solution at the beginning is very important in mixed integer linear optimization. So solvers like Gurobi and Simplex and Xpress, they put a lot of effort in finding an initial feasible solution. It's 10 times, it's an order of magnitude more important to find a feasible solution in MINLO problems, because feasible solutions do an extra bit of work, which is once you have a cutoff, an integer feasible solution, you go back to the node that represents the objective function, and you run the bound tightening of it. If you have a minimization problem, that means that this 4 suddenly became a 3. And who knows what happens if you propagate this 3 down on the whole DAG. You may get even more tightening. You may show that a lot of the feasible region is infeasible, and you held the branch and bound even more. These are not very significant statistics, but the nice thing is that this procedure, again, for 95% of the instances, that solution was found by this heuristic in the first 10 seconds. So Couenne was able to use a feasible solution in very quickly.